Well, before concluding for vector subtraction, let me tell you that the algebra of numbers, you can say the algebra of numbers, the algebra of scalars, the algebra of vectors, and also the algebra of tensors are not the essentially same. For example, in case of algebra of numbers, what actually you are doing, the plus means you are adding numbers. You are just plus, it operates for adding two numbers. In the same way, the plus, when you are making an operations, it adds physical quantities. Of course, the addition is relating to magnitude of physical quantities, but you add physical quantities essentially. Now coming to the vectors, algebra of vectors means here, better you say add operation here or the plus you are using as an operator, it leads to vector compositions, and composition is a superior way of saying over addition, in the sense that we will see in course of discussion that this composition within it carry the concept of subtraction, in the sense that both addition and subtraction are contained in compositions. Now coming to tensor, when you use the plus as an operator to add tensors, they add the tensor. Of course, the added tensor must be of same rank, whether it is a contravariant tensor or a covariant tensor or a mixed tensor, but when you add to tensor, they must be of same type. Well, it is essential to mention some of the vital concepts already we have covered before going to vector subtraction. One, let us start with the scalar. I will discuss the scalar, vector, your tensor. These are the three things I will discuss. In addition to that one, your medium and observer plays a vital role also. So before concluding anything for vector subtraction, I will have a brief exposure to these areas. Nevertheless, to make the discussion brief, I will skip the usual way of defining these terms which we have already discussed in their respective discussions, and those who have not covered like tensors and observer and your medium will be discussed in subsequent class. Now to start with the scalar, what is actually scalar? Scalars are those physical quantities, of course, possessing same value if observed with different orientations. Even if you change your looking to the quantity, the orientation means even if you with a different angle, the scalar remains the same. The physical quantity which remains the same is termed as scalar. Now to mention here, algebraic operations when you do in scalars, it is in case of a algebraic operation when you do in scalars, it is for same physical quantities. That means you cannot add density with refractive index, of course. And here to mention it that some of the scalars we can group also like density, electrical conductivity, refractive index, even moment of inertia. We can make it a group, and the other group may be of speed, mass, and like that. Making such a group is to just explain you that often the first group which I say can be equivalently termed as tensors. It is to get rid of some of the anomalies like your angles, which is not a scalar. It is because it do not qualify us to be a physical quantity. It is only a geometrical construction. So therefore, angles is not scalar. But angular velocity, angular momentum, essentially these are vectors. It is evolving with time and it is vectors. Now what is vector actually? The physical quantity which have both magnitude and direction. Can it conform to be vectors? Certainly not. It is because your AC current, your moment of inertia, they do not qualify for vectors. The reason being the vector law of compositions which we said, and usually we say it as vector law of addition is not being taken care of. So therefore, in addition to the magnitude and direction, the physical quantity must be necessarily abiding by the vector law of compositions. On the other hand, you can say instead of multiplication as product. It is because product means you can say dot product or plus product. Now, you see the vectors are generally rank 1 tensors, unlike the scalars, which are rank 0 tensors. Vectors are rank 1 tensors. Now, the vector algebra necessarily differs from either of the two cases, that is scalar as well as vector. In either case, the tensor algebra differs in the sense that when you are adding the x component of a vector A with x component of another vector B, then you are adding both the x component, but you cannot add x component of A vector with y component of B vector. Naturally, you are not doing, and it is not desirable also. But in case of a tensor, which has, you can add same rank tensors, same type of tensor you can add. It doesn't matter of coordinates, it's because tensor are space independent. It has nothing to do with space coordinates, right? Now, if you see what are the tensors actually, it is physical quantity having no specified direction, but possesses a different value in different directions. It may be, and these tensors often give rise to scalars as well as vectors. If the rank is 0, it becomes scalar. If the rank is 1, it becomes vector. And even the tensor can be neither of the two also. So examples of such tensors I have mentioned already: density, refractive index, like that, your moment of inertia, like that. Now coming to medium, you already have an idea regarding isotropic and anisotropic mediums. Isotropic obviously where physical quantity possesses same value if observed from any orientations, and those are where the physical quantity varies with direction, those we say anisotropic materials or anisotropic medium. Accordingly, the rule of physics get changed. The example of such we have seen in calculating the capacitance of a parallel plate capacitor in vacuum or in air. You have simply the C or the capacitance equal to epsilon 0 A by D, but when you replace the capacitance space, the capacitor space in between the plates by some dielectric medium, the formula becomes C equal to epsilon 0 A by D, where K is the dielectric constant. So this is how medium is also changing the rules of physics, or it is modifying, affecting also. Now coming to observer, we have a misconception by saying that observer means measuring by C. Actually, in fact, it is nothing to do with measuring by C. And this is measuring by C is a misconception actually that gives rise to the misconception. One such misconception is your length contraction, which is also a misconception. And it is nothing to do with measuring with C. What actually observer means, it is an infinite set of synchronized recording clocks distributed throughout space at rest, and accordingly the law of physics get modified. For example, when you are writing Maxwell equations in terms of the Laplacian, and when you are writing the Maxwell equations in terms of D'Alembert, there is a difference when you incorporate the tensor form in writing the Maxwell equations. Well, now coming to the vector subtraction, it is not a fundamental rule of vector algebra to say. Why? It is because when you add a vector A with a vector V, giving rise to resultant. Now if you are interested to find, do the A vector subtracting, or you say B vector subtracting from A vector, that you are writing as A vector minus B vector. it is essentially required that instead of writing in such a subtractive manner, you can write it in a composition manner, in the sense that you take minus b vector as some another vector c and then add it. So therefore, that will become now a vector plus c vector, giving rise to a resultant vectors. And you can check now that the same commutative law is valid. It is because a plus c now can be shown as a c plus a. So therefore, the way you write vector subtraction is not a fundamental way or fundamental property of vector algebra, we can say. We get the value of a minus b when theta is equal to 180 degree, or the angle between the two vectors when it is 180 degree, you are getting the difference of the two vectors. But that is not a case of vector subtractions. In fact, vector subtraction is not a fundamental rule of vector algebra. So therefore, instead of saying that it is a vector addition, we can say that vector composition, which will imbibe in the discussion both vector addition as well as vector subtraction in a very algebraic sense. So therefore, vector subtraction as such, it should not be used as a fundamental operation in vector algebra. We will discuss more regarding mathematical physics in our subsequent class. Thank you.